Hello, my name is Mario Motta. I'm a senior research staff member at IBM Yorktown, and I work on the quantum simulation of many-body systems. Today I'll be telling you a bit about the concept of Hamiltonian dynamics, which is very important in quantum computation. I'll give you an overview of some applications of Hamiltonian dynamics and of some techniques to simulate it on quantum devices, and I will suggest you some references for some more in-depth explorations. So, let's start. So, to bring everybody on board, let us first start by defining what Hamiltonian dynamics means and what it means to simulate it. So, for that, we have to go back to the postulates of quantum mechanics, which tell us that the state of an isolated quantum system evolves in time according to a Schrödinger equation, where the time derivative of the state is proportional to a state that is obtained applying the Hamiltonian of the system, the operator associated with its energy, to the state at the current time t. The formal solution of the Schrödinger equation is given by the action of a unitary operator, the time evolution operator, to the state at the initial time. For a time-dependent Hamiltonian, a Hamiltonian that depends on time, this operator is the time-ordered exponential that you see in the second equation. For a time-independent Hamiltonian, a Hamiltonian that remains constant with time, it is the exponential of the Hamiltonian times minus I at t. Simulating Hamiltonian dynamics, for example, on a quantum computer, means to map exactly or approximate the state of the system at time t on a state of the quantum computer through the application of a quantum circuit. And once we've done that, for example, we can calculate the expectation value of an observable at time t. So the problem of simulating Hamiltonian dynamics is one of the real challenges of the simulation of quantum systems, along with some others. For example, we have the simulation of Hamiltonian eigenstates, like the ground, the lowest energy, and the excited, the higher energy states of a Hamiltonian, which are solutions of a time-independent Schrödinger equation, and the simulation of thermal averages, thermal properties, which requires us to find the Gibbs state, the equilibrium state of a canonical system at inverse temperature beta. These three problems are deeply intertwined. First, they often determine together the physical properties of some quantum system. We will see an example later when we talk about scattering experiments. And second, as we will see, the simulation of Hamiltonian eigenstates may use the simulation of Hamiltonian dynamics as a subroutine or vice versa. So there are very interesting algorithmic connections between these problems, which are fairly important for quantum computing. So Hamiltonian dynamics is very important because it determines many physical properties. Let's take a look together at some applications of Hamiltonian dynamics in the simulation of many-body systems. So, one of the ways to probe material properties and to understand material properties routinely are laboratory experiments. Among laboratory experiments, there is an important class of experiments which are the scattering experiments. As an example, in the chart we can consider ultraviolet visible absorption spectroscopy. In this kind of experiment, some sample, that's the yellow thing, at equilibrium at temperature T, for example at temperature 0 when it is in the ground state, is hit with monochromatic light that has a well-defined frequency omega. The intensity of the light emerging out of the sample is recorded as a function of the frequency, giving us an absorption spectrum. Some examples from astrophysics are shown on the right. Ultraviolet absorption spectra often present dark lines corresponding to frequencies that the system absorbs. The pattern of lines is a little bit like a footprint that allows us to understand some of the properties of the material that is responsible for the absorption. For example, the chemical composition. But photons are not the only particles that we can throw at a quantum system. In condensed matter, for example, it's very frequent to use neutron scattering experiments. In a neutron scattering experiment, some quantum system, it can be a quantum liquid like superfluid helium-4 or a spin system, is hit with neutrons that have a well-defined momentum k and energy E. And what we measure is the intensity of the scattered neutrons with a different momentum, k plus q, and with a different energy, E plus delta E. A higher or a lower intensity of scattered neutrons, we see an example on the right, means that the interaction between the neutrons and the system has changed the momentum of the neutron by an amount q and its energy by an amount delta E. So there are many different kinds of scattering experiments, but they all share some common structure. In many of these scattering experiments, a quantum system is prepared at equilibrium in the ground or thermal state of some Hamiltonian, H0, and then some perturbation is applied. The perturbation represents the interaction with the impinging radiation or matter. In ultraviolet visible spectroscopy, the perturbation operator is a component of the dipole moment to represent the interaction with an electric field. In the case of Newton scattering, an external potential representing the interaction with the impinging neutrons. The absorption of a photon in UV spectroscopy with energy h bar omega is due to some excitation, if we imagine to be at zero temperature, from the ground state psi0 to an excited state psi me, with an energy difference E me minus E0 that is equal to h bar omega. And this excitation is induced by the perturbation. These notions are captured in terms more mathematically rigorous by Fermi's golden rule, according to which the absorption of UV light is described by a linear combination of Dirac deltas in the frequency peaked at the transition energies of the system with transition rates that are matrix elements of the perturbation operator between the ground and the excited state. In UV visible spectroscopy, these quantities are called transition dipole moments, and they are related with the oscillator strengths. This form is given in frequency domain, but with the Fourier transform and with the resolution of the identity, we can represent it in terms of a time-dependent response function, a ground state expectation value of the product between the time-evolved perturbation operator V and the perturbation operator V. Response functions are a very fundamental aspect of physics. They link experimentally observable properties with some underlying many-body quantum mechanical behavior, and they are also an important application for Hamiltonian dynamics because we have a time evolution operator inside the response function. If you're interested in this kind of problems, I do recommend the book by Fetter and Waleczka, Quantum Theory of Many Particle Systems. It's a fantastic reading. Fermi's golden rule that we saw in the previous chart captures essentially a linear response approximation to a more general setup where a system is prepared at equilibrium, for example at zero temperature in the ground state of an unperturbed Hamiltonian H0, and then a perturbation, possibly time-dependent, is applied, letting the system evolve and according to a time-dependent Schrödinger equation with the unperturbed Hamiltonian and the perturbation. After that, a time-dependent expectation value, A of t, is measured at some time t. Linear response approximation essentially corresponds to approximating the time evolution operator to first order in the perturbation operator V, and accordingly the time-dependent expectation value differs by the value at the initial time to an amount that is controlled by a correlation function between the observable A and the perturbation operator V. The setup of points 1, 2, 3 is also the setup of quantum quenching experiments, which are used to study aspects of non-equilibrium physics such as thermalization and universal aspects of critical dynamics. In this kind of setup, one doesn't require that the perturbation be weak. In other words, we don't need to approximate the time evolution operator in any way in principle. So now we have seen some quite important applications of Hamiltonian dynamics, which, for example, defines the time-dependent response functions and time-dependent expectation values, which are probed in various experiments. Along, of course, with the problem of preparing Hamiltonian eigenstates, such as the ground state, which also was in all these quantities. We briefly discussed two kinds of spectroscopy experiments, but there's a great variety of them for different systems and situations. But how can we simulate Hamiltonian dynamics on a quantum computer? That's the topic of the next part. So the first thing we have to do is to map the degrees of freedom of the problem to the degrees of freedom of the qubits, and for that I remind you to Kevin Sung's lecture. This essentially means that we can represent the Hamiltonian of a physical system with a qubit operator, and in principle the time evolution operator with a unitary qubit operator as well. In practice, the simulation of the time evolution is performed by some quantum circuit, which we will call V of t, and this quantum circuit approximates the time evolution operator u of t e to the minus th for a time-independent Hamiltonian with some accuracy epsilon. This, referring to the chart, means that time evolution starting from a given point psi 0 would lead you to some state psi of t. If you have an approximation, if a quantum circuit implements an approximation v of t to the time evolution operator u of t, you're going to land into a different state, psi bar of t, for example. And the accuracy of the simulation can be, for example, quantified by the distance between the two states, epsilon, which of course you would want to be small. The simulation is efficient if the number of elementary gates, 1 and 2 qubit gates, in the circuit V of t scales at most polynomially with respect to the number of qubits, system size, the desired precision, or accuracy, and the evolution time. A great discussion about these topics is inside Andrew Child's PhD thesis, which is referenced down here. So before going into something more rich, let us stop for a second and make one example. A Hamiltonian that is comprising only one Pauli operator, here at the top. The exponential of this Hamiltonian, we can compute it efficiently and exactly for any value of the time. First, we can transform the Pauli operator into a tensor product of Z operators using layers of single qubit operations. For example, for the Pauli X operator, we can use the Hadamard to convert into Z form. After that, our goal is that of implementing the exponential of a tensor product of Z operators. And it is known that that can be done with two ladders of C0 gates surrounding a single qubit Z rotation of an angle that depends on the evolution time, but also the coefficient in front of the Pauli operator. So this is a simple example of a Hamiltonian for which the dynamics can be implemented exactly, no approximations, with a linear number of elementary gates and for a generic time, no matter how long. It's of course a special case. Another example is that of one-body fermionic operators. I refer you again to Kevin Sung's lecture, which explains very well how to map these fermionic operators onto qubits. On the top here we have a one-body operator with its creation and destruction operators acting on m spatial orbitals. even for this operator, the exponential e to the minus ith can be computed efficiently and exactly for any time. And the reason is that a one-body fermionic operator can be diagonalized exactly by the exponential of a one-body operator, an operation also called an orbital rotation or a Bogoliubov transformation. So we can write our Hamiltonian as the product of a Bogoliubov transformation, another Bogoliubov transformation, and in the middle a diagonal one-body operator, so a linear combination of number operators multiplying the eigenvalues of the operator. The orbital rotation can be implemented with a circuit that has a linear number of z rotations and a quadratic number of 2-qubit xx plus yy gates. You can see an example down here for 4 orbitals. The exponential of the diagonalized one-body operator, because number operators in Jordan-Wigner representations are single qubit z operators essentially, can be implemented with a single layer of z rotations. And then we have again another Bogoliubov circuit to implement the inverse of the Bogoliubov transformation. So with this kind of scheme, one achieves an exact solution with a polynomial number of gates for a generic time. Once again, a consequence of the fact that we can exact diagonalize one-body operators. It is often the case that the Hamiltonian is not an operator for which we can efficiently simulate the dynamics exactly. We have to introduce approximations. However, if our Hamiltonian is a linear combination, as it is often the case, of terms hi, each of which can be simulated efficiently, then also the Hamiltonian itself can be simulated efficiently. A way to prove constructively this fact are product formulas, product formulae. Product formulae are a class of formulae that approximate the time evolution operator for the Hamiltonian using products of the time evolution operators of the individual terms of the Hamiltonian, hi, hence the name product formulas, of course. Before showing some product formulas, let us make some general observations. The first ingredient of a product formula is always to break down the time interval, 0 to t, into some number of steps, ns, typically of equal duration, t over ns. The time evolution operator for a single step is then approximated using products of the exponentials of the hi terms with an error that scales like some power of the time step. And the error of the product formula decreases to 0 when the number of steps increases. This is, informally speaking, because the error per step decreases very quickly with step length, compensating the accumulation of errors for ns steps. For interested readers, there's a very thorough discussion and presentation of the errors of product formulas in this Physical Review X paper. The arguably simplest product formula is the sometimes called primitive approximation. In the primitive approximation, the time evolution operator for a single step, u delta t, is approximated simply by the product of the exponentials of the individual operators times delta t, which we assume we can compute exactly or with very accurate approximations. We saw it being the case for Pauli operators and one-body fermionic operators. Those are examples of individual terms for which we can simulate the dynamics exactly. The primitive approximation is an approximation because if we expand both u of delta t, the exact single-step time evolution operator, and v of delta t, its approximation, in powers of the time step, we find that the two Taylor series differ, and they differ at the second order. The distance between the two unitary operators, which bounds the distance between the final states, the accuracy of the simulation for a single time step, grows quadratically with the time step times a coefficient which is essentially the norm of a sum of commutators. The simulation for a time t, broken down into ns intervals, reaches accuracy epsilon when the number of steps scales like ct squared over epsilon. The cost grows quadratically with time and is proportional to 1 over epsilon. However, the simulation is efficient so long as the number of terms L grows polynomially, and so does C. There are many more refined product formulae that use more gates per steps, but achieve a better error than the primitive one, thereby requiring fewer steps and therefore fewer gates than the primitive approximation on a whole. For example, the second-order Suzuki approximation is a product formula that uses the exponentials of the individual terms from 1 to L times delta t over 2, followed by the product of the same exponentials from L to t. If we compare the Taylor series of the exact time evolution operator and of the Suzuki approximation, we find that the error scales like a third power of the time step, which is better for a small time step than the second power. So the second-order Suzuki approximation uses essentially twice as many gates per step compared against the primitive approximation, but on the other hand, the number of steps required to achieve the same accuracy epsilon now scales like t to the 1.5, lower than t squared, times the square root of 1 over epsilon, which is more favorable than 1 over epsilon. And the simulation is efficient under the same assumptions as for the primitive approximation. So before moving on to something different, let's stop for a second and make a couple of examples. The first one is a two-site Ising Hamiltonian, which we can see here in the top portion of the chart. This is a linear combination of 3 Pauli operators, and we can simulate its dynamics, for example, with the primitive approximation, where we have the exponentials of the individual Pauli operators. The exponentials of the x operators can be executed in parallel, so to speak, meaning at the same time on the two different qubits with x rotations. And the exponentials of the ZZ interaction with the ZZ rotation, which, as we have seen in a chart before, requires 2 C-naughts and a single qubit Z rotation. So that's an example of a primitive approximation. Another example, again connected to Kevin Sung's lecture, is that of the electronic structure Hamiltonian, the Hamiltonian of electrons in the molecules. The electronic structure Hamiltonian is the sum of a one-body operator and of a two-body operator. Now, of course, we could represent this Hamiltonian as a linear combination of Pauli operators and then simulate its dynamics with a product formula for a linear combination of Pauli operators. That would be possible, but the cost per Trotter step would be roughly order a fifth power of the number m of orbitals. This is because there is going to be m to the fourth Pauli operators, and the exponential of each requires roughly order m 2-qubit gates. A lower scaling comes from a low-rank decomposition, for example. It has been known for a long time that the electron repulsion integral, the two-body part of the electronic structure Hamiltonian, can be written as a contraction of rank 3 tensors. The number of terms in the summation, very importantly, grows linearly with the number of orbitals in the system. A pictorial representation is here on the right. Instead of having a dense rank 4 tensor, we have a contraction of rank 3 tensors. If we plug in this decomposition of the two-body operator inside the electronic structure Hamiltonian and we rearrange the elements of the two-body part, we find that the electronic structure Hamiltonian can be written as the linear combination between a one-body fermionic operator, which does contain the electron repulsion integral, and then a sum of squares of one-body operators constructed with the tensors of the low-rank decomposition. These sorts of decompositions are very well known in classical electronic structure, and they have been used to obtain lower scaling simulations of electronic structure on quantum computers, but also to obtain efficient and noise-resilient measurements. A few references are here. We have essentially written the electronic structure Hamiltonian as a linear combination of operators that can be individually diagonalized by means of Bogoliubov transformations. And so this is the starting point, for example, for a primitive approximation. For each of the terms of the Hamiltonian, we apply the Bogoliubov transformation, then we apply the exponential of the diagonal part with a single layer of z rotations for the one-body part and with something more complicated, z rotations, we'll see it in a second, for squares of one-body operators. Then we apply the inverse of the Bogoliubov transformation and we loop through all the terms in the Hamiltonian. The computational bottleneck are the exponentials of the squares of the one-body operators, which require a quadratic number of 2-qubit gates, z rotations, arranged in a circuit of linear depth. An important aspect is that the z rotations require all-to-all connectivity. If our device doesn't have all-to-all connectivity, meaning we can apply physically a 2-qubit gate among all possible pairs of qubits in the device, then we have to use a swap network to move around the qubits until they become physically adjacent. Then we can apply a z rotation and then we can separate them back. I show you an example of a swap network, fairly dense one, in this chart. The development of swap networks is a very important aspect of the compilation of quantum circuits and a very fascinating one. So one thing that we may have noticed looking at product formulas is that the cost as a function of time grows more than linearly. We have a square for the primitive approximation and 3/2 for the second order Suzuki. A question now arises, can one further lower this scaling, make it linear or even lower? For a generic Hamiltonian, the answer is no. There is a very important result, the no fast-forwarding theorem, which is presented in these papers by Berry et al. And Childs and Kothari, according to which for generic Hamiltonians, the simulation of Hamiltonian dynamics scales at best linearly in time. We have seen exceptions, single Pauli operators, one-body fermionic operators, which have this property of a cost independent of time coming from their very simple diagonalization. In general, we can expect a cost as per the product formulas that grows at best linearly with time. A question is whether one can achieve a simulation time that is strictly linear in the time itself. There are some very fascinating, rather advanced approaches to Hamiltonian dynamics that I will flash out for you. One is the approximation of the time evolution operator with a truncated Taylor series introduced by Berry et al., which reaches a computational cost linear in the time multiplied by the one norm of the Hamiltonian with some logarithmic corrections that have together the time and the accuracy. There is also the so-called qubitization approach that approximates the time evolution operator with a truncated Jacobi-Unger series using a sophisticated intermediate, the construction of a special transformation called the qubiterate. And qubitization achieves linear cost in time and an additive correction, logarithmic in the accuracy. This is from Guangao Lo and Isaac Chuang. I invite you to examine these references. These are very fascinating advanced algorithms for Hamiltonian dynamics. An extra comment, we have seen how to approximately map the time evolution operator of a quantum system onto a quantum circuit, and that makes it very easy to compute time-dependent expectation values. What about correlation functions that we have seen at the beginning for the scattering experiments? These are less straightforward. These are not ordinary normal expectation values of operators. They are expectation values of products of operators, one of which is time evolved. Computing a response function requires, first of all, a ground state preparation. We have to have the system prepared in the ground state to compute the response function, a time evolution, and then a particular quantum circuit called the modified Hadamard test, which involves controlled application of the operators in the correlation function, which we are assuming to be unitary in this setting, controlled by the state of an auxiliary qubits for which the sigma minus the de-excitation operator is then measured. This algorithm was introduced by Somma et al., and since then there has been a great deal of research in trying to economize it. Some references are here. In particular, there's one by Mitarai and Fuji that makes use of an ensemble, a collection of unitary transformations and mid-circuit measurements to bypass the need for the auxiliary qubit and the controlled operations. So we have seen that Hamiltonian dynamics is important for applications like scattering experiments, and that there are very nice algorithms like product formulas to simulate it efficiently and accurately. One could even argue that Hamiltonian dynamics is a quintessential application for a quantum computer. In more formal terms, this idea is captured by the BQP completeness of the Hamiltonian dynamics. BQP is short for bounded error, quantum polynomial time. It's a concept that is defined formally in the framework of the theory of quantum computational complexity. It's a very rich, advanced topic beyond the scope of this presentation, so I will give you an informal discussion, but refer you, if you are interested, to this very good book by Alexei Kitaev, Shen and Viali, Classical and Quantum Computation. Informally speaking, BQP is the class of problems that a quantum computer can solve with polynomial resources and a high success probability. Since we have seen that for many Hamiltonians there are algorithms like product formulas to simulate Hamiltonian dynamics with polynomial resources and a controllable accuracy, we can informally say that Hamiltonian dynamics is a problem in the BQP class. But there's something more. Hamiltonian dynamics is BQP complete. This means that any other computational problem in the BQP class can be reformulated as the problem of simulating the dynamics of a suitable Hamiltonian. The first to realize this circumstance and to offer a proof was Feynman in his seminal 1980s papers. Two of them are here. And it is for that reason that quantum computers are sometimes presented as Feynman's vision, the vision to use a device operating according to the laws of quantum mechanics to simulate the dynamics of, for example, a many-body Hamiltonian. So Hamiltonian dynamics is important for certain applications like the scattering experiments. It is BQP complete, so it's a very compelling application for a quantum computer. And this, to me, is one of the most fascinating aspects of quantum computing. Hamiltonian dynamics also has deep algorithmic connections with other quantum simulation problems. and I will cover this topic a bit in the last part of the presentation. So back with the mind to our initial diagram. In particular, what I will discuss is that Hamiltonian dynamics can be used as a subroutine in algorithms for the preparation of Hamiltonian eigenstates, like the ground state, the lowest energy state, and the low-lying excited states. But first, I shall give you, let's say, a disclaimer. The problem of computing Hamiltonian eigenstates is fairly different from that of simulating Hamiltonian dynamics. In particular, it is not in BQP. It is in another quantum computational complexity class called QMA, which is short for quantum Merlin-Arthur. Again, I will give you an informal discussion, but I refer you, for example, to the book by Kitaev if you have interest in this topic. QMA is the class of problems whose solution can be verified, though not in general produced, by a quantum computer with polynomial resources. For many Hamiltonians, the eigenstate problem is in the QMA complexity class, so we can consider it, in a worst-case scenario, a hard problem even for a quantum computer. A very important reference in this regard is this paper by Kempe et al. In more informal terms, a normal user, someone with polynomial quantum resources, akin to King Arthur in this metaphor, can verify that some wave function is the solution of the Hamiltonian eigenvalue problem. But in general, one cannot guarantee that such a normal user will be able to produce that wave function. The production of that wave function, in a general case, may require up to exponential resources that only an exceptionally powerful agent, represented by Merlin, possesses, hence the denomination QMA. And so quantum algorithms for eigenstates are heuristic in nature. They unavoidably give approximated results, often very accurate, but there are regimes in which they may break down. And identifying and understanding these regimes is very important. The first algorithm for Hamiltonian eigenstates based on Hamiltonian dynamics that I will present to you is adiabatic state preparation. In adiabatic state preparation, we are given a Hamiltonian, which is the sum of an unperturbed term, which has known and efficiently preparable ground state, and of a perturbation V, which makes the Hamiltonian complicated. We can think about the electronic structure Hamiltonian with its one and two body part. The goal is to prepare the ground state of the full Hamiltonian H, not of H0. The adiabatic method is based on the adiabatic theorem of quantum mechanics. If a system is prepared in the ground state of a Hamiltonian, and then the Hamiltonian changes slowly, then the system remains in the instantaneous ground state, meaning the ground state of the time-dependent Hamiltonian, under certain conditions. So the idea is that if we slowly transform the Hamiltonian from H0 to H, we will have the ground state of H0 evolving into the ground state of H. I recommend this science paper by Fari, pioneering work in the field of adiabatic state preparation. In more precise terms, we have a time-dependent Hamiltonian that interpolates between H0 and H, for example, with a linear form, and then a quantum computer that obeys a time-dependent Schrödinger equation and starts in the ground state of H0. Starting from the ground state of H0, we converge to the ground state of the Hamiltonian when we increase uppercase T, the total simulation time. When the total simulation time increases, the transition from H0 to H becomes slower and slower. This is true provided that the Hamiltonian remains gapped. In other words, the distance between the ground state of H, the target Hamiltonian, and the final point of the adiabatic state preparation of this time-dependent Schrödinger equation is bounded by 1 over the time, and then some combination of factors that have inside the time-dependent gap, the energy difference between the ground and the lowest excited state. If the Hamiltonian remains gapped throughout the whole adiabatic state preparation, then with a finite time we can converge very close to the ground state. If along the adiabatic path the Hamiltonian becomes gapless, we have a divergence, and this cannot be guaranteed anymore. So we can think that the vanishing of the gap is a manifestation of the QMA nature of the ground state problem in the framework of adiabatic state preparation. How is adiabatic state preparation implemented in practice? For example, we can solve our time-dependent Schrödinger equation with a product formula. Here, for example, we use a primitive approximation where the path from 0 to t is broken into ns steps. The Hamiltonian is approximately considered time-independent in each step, and the exponential is approximated by the product of the exponentials of v and h0. This, of course, requires that both h0 and v are efficiently simulable. We also notice that the coefficient in front of the perturbation grows in size as the adiabatic state preparation unfolds. The adiabatic state preparation algorithm does use Hamiltonian dynamics as a subroutine to approximate ground states. There are two observations. One is that the simulation time may scale unfavorably with system size if we have a gap shrinking or closure. And second, to achieve a certain accuracy, we need a sufficiently large number of steps. And on a near-term device, that may mean a very deep circuit or one with many gates through which errors accumulate. Therefore, it becomes desirable to approximate the ground state with some shallower circuit. How can we do that? An answer is given by the QAOA, which is short for Quantum Approximate Optimization Algorithm method. QAOA, again I refer you to a paper by Fari et al., is very similar to adiabatic state preparation, except the coefficients in the adiabatic state preparation wave function, marked here in red, are replaced with free parameters, the betas and gammas that you see down here. So the energy, the expectation value of the target Hamiltonian over the QAOA wave function as a function of the parameters gamma and beta, has favorable properties. But first of all, it can be optimized variationally with respect to the parameters gamma and beta, starting, for example, from the values corresponding to the adiabatic state preparation. It is always an upper bound to the ground state energy. It gives us a variational estimate. And the lowest energy, the minimum over gamma and beta for a given number ns of slices, decreases monotonically with ns. So the number of steps now is no longer dictated by the arguments of adiabatic state preparation. It's a parameter, a discrete parameter, and we can increase it or decrease it to capture a balance between the accuracy that we want and the error rates that form our computational budget. QAOA is another algorithm for approximating the Hamiltonian ground state that uses Hamiltonian dynamics as a subroutine, this time in a very surprising way to define a variational ansatz. And there are other examples of that in the literature. I will end my presentation discussing another algorithm for ground state approximation and Hamiltonian measurement based on Hamiltonian dynamics, the quantum phase estimation method. In the traditional setting, we assume that the register of qubits is prepared in an eigenstate, lowercase u, of some unitary, uppercase u, and our goal is to find the corresponding eigenvalue, which is written as e to the I 2 pi lambda for some number lambda between 0 and 1. QPE is therefore a technique to measure the unknown eigenvalue of a unitary operation, for example, the time evolution under a Hamiltonian, assuming the availability of an eigenstate. QPE achieves this goal by attaching m auxiliary qubits to the main register, preparing them in an equal superposition of all the 2 to the m bit strings or computational basis states. Then controlled powers of the unitary u are applied conditional to the state of the auxiliary qubits. Since the main register is in an eigenstate of the unitary, the controlled unitaries apply phases to the computational basis states of the auxiliary qubits. After a Fourier transform, the auxiliary qubits are measured, yielding some integer L between 0 and 2 to the m minus 1. The probability distribution for the measurement is picked around an integer, lambda tilde. Who is this integer? Well, we can write lambda, essentially the log of the unknown eigenvalue, as lambda tilde over 2 to the m plus delta. And in other words, we can think that lambda tilde is an integer approximation to 2 to the m times lambda. The higher the number of auxiliary qubits, the more precisely we can therefore nail down lambda through lambda tilde. The probability to measure lambda tilde is bounded by 4 over pi square, 0.4, for any value of m. So we obtain lambda tilde, the integer approximation to lambda times 2 to the m, with a very high probability. I can very much recommend you the Qiskit implementation of the quantum phase estimation algorithm as a very compelling learning opportunity, as a way of understanding it more deeply and also experimenting with it firsthand. But now you could say, okay, but you haven't told me how to obtain the eigenstate. QP is fantastic. If I have the eigenstate, I can measure the eigenvalue. But in general, an eigenstate of a unitary transformation may not be available. And that's the case for time evolution, where the eigenstates are also the eigenstates of the Hamiltonian. What we can have is an input state that can always be written as a linear combination of the eigenstates of U with some coefficients. If the input state is a good approximation to the unknown target eigenstate, then the Cu coefficients are picked around some particular value of U. Otherwise, they are just very broadly distributed. When quantum phase estimation is run with this initial state, the probability distribution has multiple peaks, each centered at an integer approximation, lambda tilde u, of a multiple of lambda u, log of the unknown eigenvalue over 2 pi. And the height of those peaks is controlled by the absolute value squared of the coefficients Cu in the expansion. So if with the probability proportional to the square modulus of Cu, which is I if psi is close to the eigenstate u, the integer lambda tilde u is measured and the qubits collapse into an approximation of the eigenstate u. So far we have said very little about the unitary, but that can, for example, can be the time evolution operator or some approximation obtained through a product formula. So quantum phase estimation shows us something very profound, that Hamiltonian dynamics can be used as a subroutine to measure the Hamiltonian, but also to probabilistically prepare Hamiltonian eigenstates. Of course, for a high probability of success, we need coefficients picked around the target eigenstate, which in a worst-case scenario may be difficult to achieve due to the QMA nature of the Hamiltonian eigenstate problem, but that can be the case thanks to other approximate heuristic algorithms like adiabatic state preparation or QAOA. And so, in summary, I tried to convey a sense that Hamiltonian dynamics is very useful to interpret and ideally to predict the outcomes of certain experimental observations, for example, scattering experiments and quantum quenches. It is also a very compelling application for a quantum computer because it is BQP complete, and it is also a surprisingly useful subroutine in the search for Hamiltonian eigenstates, as we have seen through the examples of adiabatic state preparation, QAOA, quantum phase estimations, and even other algorithms. I leave you with a few additional references. On the right, 5 review papers that talk about quantum simulations of many-body systems, from spins to chemistry with various algorithms, including a focus on Hamiltonian dynamics, and a textbook of which I happen to be a co-author, which follows the logic of this presentation and tries to be as extensive as possible with regards to calculations, explanations, examples, and supporting material like figures. With this, I thank you very much for having attended this presentation, and hopefully you will think about Hamiltonian dynamics in your studies and in your research. Thank you.